Welcome to this video about solving trig equations. So in this first example, we have the equation sine x plus square root of 2 is equal to negative sine x. Now this is an actual equation, so that's different than what we've been doing, which was solving and really verifying trig identities. This is an actual solution. Okay, so I can do whatever I want. I can add sine x to both sides, which I'm going to go ahead and do. So then I've got 2 times sine x is, I'm going to subtract square root of 2 from both sides. Okay, so now I'll go ahead and just divide by 2. So we've got sine of x is equal to negative square root of 2 over 2. And we can think about the unit circle. The sine is negative in quadrants 3 and 4, and so we would have these angles right down here. Okay, so at 5 pi over 4 pi over 4 and at 7 pi over 4, because sine is related to the y value of those points. So let's see, we've got 5 pi over 4. Okay, and x equals 7 pi over 4. But don't forget that from this point, I could just go around the circle once. I could just add 2 pi, or I could add another 2 pi. Okay, so any integer multiple of 2 pi would get us right back to that same spot who has a sine value of negative square root of 2 over 2. Okay, and likewise for this other point. Okay, so there's both of our solutions, and we've listed every single possible one that we could get there. All right, so let's go ahead and go into Desmos and go ahead and graph. Okay, so if we have the sine of x, okay, and then we have plus plus, it was the square root of 2, so square root of 2. All right, so that's the left-hand side of our equation. And now to find out where they meet, so we just need to add another equation, which is the right-hand side. So it would be the opposite of sine x, is our other one, sine of x. Okay, and so we can start looking and seeing there's a solution right here, and a solution here, and a solution here, and oh, that one's not. Okay, but right, it's any time that these lines intersect, and so you can see as we zoom out and out, there's an infinite number of intersections there. Okay, so let's try another one. Okay, so on this next one, these are going to be a tiny bit quite a bit fewer solutions. So we're going from infinite number of solutions down to a finite number of solutions because we're limiting our interval. Okay, so here we've got 2 sine x minus 1. So I'm going to isolate my trig function. So we've got 2 sine of x equals positive 1, and then dividing through by 2, we get sine of x is equal to 1/2, and sine is the y value at terminal points, and sine, the y values are positive up at quadrant 1 and 2, and sine is 1/2 at pi over 6 and 5 pi over 6. So x equals pi over 6 and 5 pi over 6. Now if we went around the unit circle, if we went around from pi over 6, we'd get to 6 pi over 6 plus another 1. Okay, let's see, so getting right back to the beginning, that's 2 pi, and we could think of, since we're in 6th, that could be 12 pi over 6. Okay, so then if we add this extra one, this spot would be 13 pi over 6. and we're limited. We're supposed to stop at 2 pi. So we don't have to add any more increments there. Those are the only two solutions that work. Okay, we'll try this next one. Let's see if I can move my graph. Okay, so isolating my trig function, I would get 3 tangent squared x is equal to 1, and dividing by 3, we would get tangent squared x is equal to 1/3. And then when we go to take the square root, we would get tangent of x is equal to the positive or negative, let's see, square root of 1/3. And we're used to rationalizing that and just seeing what that is. So that would be either positive or negative square root of 3 over 3. So that's a lot of possibilities. We could be in quadrant 1 or 3 for positive tangents. That's pi over 6. And there's 7 pi over 6. But we could also have it be negative. So that's 5 pi over 6 and 11 pi over 6. And we get to stop, that same quadrant said we get to stop at 2 pi. So x equals pi over 6, 5 pi over 6, 7 pi over 6, or 11 pi over 6. Okay, we're going to still use that same interval. We're going to go from 0 to 2 pi. And okay, so I'm going to go ahead and subtract 3 from both sides of 2x is equal to -3, and then dividing through by 3, we get the tangent of 2x is equal to -1. Okay, and then we think about our unit circle, and where does tangent have a -1 value? That happens at 3 pi over 4 and at 7 pi over 4. Okay, so that means that our angle here is either 3 pi over 4 or 2x is 7 pi over 4. Okay, and now we need to solve for x. So I'm going to just multiply both sides by 1/2, so we get x equals 3 pi over 8. And same thing here, we get x equals 7 pi over 8. But we need to add multiples of the period. Okay, let's see. What is the period? When there's a coefficient in front of the input there, that affects the period. All right, so period for tangent is usually pi, but we have to divide by that coefficient of x there, by that 2. Okay, so we're going to add periods, and any full rotation, so any multiple of pi over 2 would get us right back around. Okay, which means that our tangent would have the same output. Okay, now just one little thing. This is in eighths. I'm just going to go ahead and write these equations in eighths. So this would be plus 4 pi over 8 times some multiple. Okay, or my other one is at x equals 7 pi over 8 plus 4 pi over 8 times k. All right, well, my job is to list every single possible solution. There's one. X equals 7 pi over 8. There's the next one. Okay, well, what's the next one after this? Okay, let's say that we went one full rotation. Okay, so if we said we're going to add one rotation here, that would mean that we would take our original point, 3 pi over 8, plus one rotation, do it just only once. Okay, so that gets us to 7 pi over 8. Well, I already have that one. Okay, so let's try this again. Okay, so 3 pi over 8. And let's do 2 rotations. All right, so here we go. Here's my period. Go around twice. So that would get us to 11 pi over 8. Okay, next one. And we just need to keep on going until we hit 2 pi. And 2 pi in eighths would be 16 pi over 8. Okay, so we're not quite done. Let's keep going here. So let's try adding a third rotation. Okay, so I start with my point. I add the period, and I'm going to fly around that thing 3 times. Okay, so this would get me 12, 15 pi over, or pi, that's a pi, over 8. 15 pi over 8, and that is as far around as we can go, because if I added another 3 pi over 8, we would be past 2 pi. So we're finished. Okay, so let's look what we did, because these can be confusing. Okay, so first we just solved the equation right here. We isolated our trig function and we solved for x. Okay, then we wrote down, thinking about the unit circle, what angle would produce this output. Okay, so that's how I came up with my new equations without a trig function, because I was evaluating the angle for a specific output of -1. Okay, then the next step is, now we went and we thought about our period. And so we added multiples of the period, and then you just have to kind of go through around and around and around, adding rotations as you go to list all of those points. All right, and we could stop, we knew to stop here because we were told that we needed to stop at 2 pi. So then at that point you know that you're done and you have all of the ones that you need. All right, in this video we're going to look at solving trig equations, and this is something that really comes up a lot in biology. So this example is looking at, it's a made-up example, but it is representative of a lot of data that will come up in biology. So let's say that there was a population of wolves in the same area with a population of rabbits. So we have the two equations, and then I went ahead and graphed these. And so we need to use the graphs to determine if there will be a time when they will have the same population. Okay, so let's kind of look at this. Let's look at this and the equations too. Okay, so the rabbits have a pretty high initial value there, right? So this is the rabbits. And it's a sinusoidal function, but it's been moved over to the left a little bit. So that's kind of the beginning of our sine function, then it moves down. All right, and now for our wolves, this is their initial value is right down here. So quite a few less wolves. And we can see that they never overlap. So if this is the total population on the x-axis, and then this is time in months, you can see that it's cyclic. So